We have a very different kind of epistemic access to the past than the kind of epistemic access we have to the future. Okay, if I want to know what I'm going to have for breakfast tomorrow, that's a very complicated calculation I have to do that involves most of the elementary particles in the universe, or at least within my light cone, so on and so forth. If I want to know what I had for breakfast yesterday, it's the easiest thing in the world. Nobody needs any training in physics in order to do that. You simply remember.
Hello, this is Robinson Earhart and Pins here with the introduction to Robinson's podcast number 189. And this episode is with two regulars, also BFFs, with the last two guests way back on episode 188. One episode ago, David Albert and Barry Loewer. And David is the Frederick E. Woodbridge Professor of Philosophy at Columbia University, director of the Philosophical Foundations of Physics program at Columbia, and also a faculty member of the John Bell Institute for the Foundations of Physics, the last of which Barry is also, in addition to being Distinguished Professor of Philosophy at Rutgers. And this is Barry's second time on the show. In episode 83, we talked about probability and laws of nature, both of which figure heavily in this episode. And this is David's award-winning sixth appearance on the show. I'm going to list them all. He was on episode 23 with Justin Clarke-Doane on metaethics and absolute space. Episode 30, I was also saying a solo episode at the same time. So a solo episode, episode 30 on the philosophy of time. Number 67 with Tim Maudlin on the Foundations of Quantum Mechanics, who Tim was on the last episode 188. 106 with Sean Carroll on Many Worlds and Fine Tuning, and then a solo episode 157 on the metaphysics of quantum mechanics. But in this episode, we talk all about the terrifically named Mentaculus, which is David and Barry's joint project on foundations of statistical mechanics, and which provides a guide for how to think about and how to solve problems involving probability, determinism, free will, cosmology, time, the laws of nature, and probably consciousness. I don't think we talked about consciousness, but a lot more. It's a probability map of the universe. It's got to help out with pretty much everything. A book that Barry, Brad Weslake, and Eric Winsberg have edited on essays concerning David's book, which Barry praises in our episode, Time and Chance. Their book is called The Probability Map of the Universe, and that came out around this time last year. The link is in the description, along with David's last book, A Guess at the Riddle. And let's see what else I should say. I should give a shout out to the John Bell Institute for the Foundations of Physics. There will be a link to that in the description as well. If you're enjoying these conversations, please consider donating. The JBI could use that. There's also a Patreon for ad-free episodes and show notes, reviews, comments, likes, subscribes. These are also always very helpful, and you'll notice this wonderful shirt from Robinson's Fashion Empire, which you can also find through the description. So without any further ado, I hope you enjoyed this conversation as much as I enjoyed having it with Barry and David. Today, though, I spoke about this a little bit with Barry when I did our solo episode, but that was definitely over 100 episodes ago. So we should just pretend as if that never happened for the moment. But what I wanted to talk about was your joint framework, the Mentaculus. And maybe before we get into the actual project, we can just talk a bit about how you came upon the name.
That's a Barry story.
Yeah, I'm afraid it is. So I'm really good at naming things. I think. Not sure about other things, but there's a film by the Coen brothers called Serious Man. It's about a physicist who's going through a midlife crisis. I won't describe it more, but it's definitely worth seeing. It's a good, very good movie. And there's a minor character in there who's scribbling in a book, and someone says, "What is that book?" And he says, "It's the Mentaculus." And he gets looked at, and the person says, "What is that?" And he says, "It's a probability map of the universe." And when David was writing Time and Chance, he and I were in communication. And one of the things that really struck me about it is the way he's thinking about statistical mechanics, which I knew something about, but not nearly enough, is that it really led to something like an assignment of probabilities, conditional probabilities over everything, if one were to take it really seriously. And I thought that's a gold mine for philosophers. So I decided to name this project the Mentaculus.
As our viewers can see on your beautiful shirt.
Now, can they actually see the shirt and thing? So I taught a summer school, twice actually, but 2 summers ago, which there are a lot of people in at the Central European University Summer School, which is located in Budapest, despite the terrible Prime Minister of Hungary kicking the Central European University itself out of Budapest. The summer school is still there, about laws and probabilities and the Mentaculus. And I gave to all the participants in the summer school these T-shirts. And David has a T-shirt too, but he refuses to wear it.
Well, speaking of David and speaking of his book, Time and Chance, I think we should start with a very basic, though quite big question, and it's how you think about chance, the difference between objective and subjective probabilities. And I don't think that we should just assume that our listeners are familiar with the distinction.
Well, the first thing I would mention is there's an excellent Stanford Encyclopedia article about interpretation of probability by Alan Hayek, another good person to talk to, incidentally. And he, reviews the various ways about thinking about probability. And as Ian Hacking, who wrote a great book called Emergence of Probability, says that at the very beginning, probability was a Janus concept, has two faces, one looking to the mind and the other looking to the world. And the way probability got to be thought of over its history was by emphasizing one or the other, and sometimes trying to combine these two aspects. So one is an objective account. There's something about the world that makes probability claims right or wrong. And the other is probability is just about what your degrees of belief or your credence should be in various claims about the world. And of course, these are related. And David Lewis, who thought a lot about this, formulated a principle saying how they should be related that has gotten to be called the principle, main principle about chance. And there's been a large literature in philosophy about the principle, whether it's compatible with his Humean account of chance or not, and if it's not, how it should be modified, and what might justify it, and so on. The subjectivist account of probability is basically based on what a person's degree of belief in a proposition might be, and that was suggested that could be determined by seeing how a person would bet on that proposition. Frank Ramsey actually formulated this really clearly, and later Di Finetti developed a whole theory about it, and Leonard Savage, another statistician, wrote a book about it. And basically the idea is that if we saw what odds people would take in various propositions, we could see what their degree of belief in that proposition would be. So take like the proposition that there's life on another planet within a few light years of the Earth, let's say within 10 light years of the Earth. I have a certain degree of belief in that. What is it? Well, ask me myself, what would I bet? How much would I risk in order to win? How much to win, let's say, $1? Would I risk 50 cents, 70 cents to win $1? If I'd only risk 50 cents, then my degree of belief would be less than a half to win $1, a third. The objective account of chance, something about the world, that usually got identified with something like frequencies. How often some event would occur on some kind of experiment or trial. So like probably the coin landing heads of a coin landing heads is the frequency of its landing heads, given that it flipped a certain number of times. But of course, most events and most experiments happen only a finitely many times. And we don't know what experiment should we be talking about? What trial should we be talking about? Sometimes this has been expressed as a hypothetical frequency account in terms of counterfactuals. What is the frequency of the coin landing heads if it were to be flipped many, many, many times? But there are a lot of problems with these accounts, as you could read about in Al Hayek's entry in the Stanford Encyclopedia. David Lewis suggested what I think is a genius idea about how to think about chance connected to his account of laws, but I'm not going to go into a big story about that now because it would take up too much time. But it's connected with his Humean account of laws. And the basic idea is that the fundamental laws assign probabilities based on what probability law fits the world the best. Lewis thought that probabilities apply only dynamically when the fundamental laws are indeterministic. He didn't realize that his very idea could be applied even when the fundamental laws are deterministic, because then you could just end up assigning probabilities over possible initial conditions compatible with the dynamical laws. And this is a great idea and allows probabilities to be assigned to theories that are deterministic, like statistical mechanics in its classical form, or Bohmian mechanics, and various other things. And insofar as I think I've made a contribution to this subject, this is certainly the main one, is that I saw that this was true about Lewis's account of probability and wrote some papers about it. And when I showed Lewis it, he said, "Oh, I see." But then he died shortly after that.
David, do you have anything to add?
I mean, just I think Barry spelled things out pretty eloquently. I assume the reason you brought up this question is to allow us to make the point that the kinds of probabilities we're thinking about when we talk about the mentaculus are definitely the objective physical kind, the kind that one attempts to analyze in terms of frequencies or in terms of connections between, the structure of the laws, like Barry was talking about, and so on. However one succeeds in analyzing it, those are the kinds of of probabilities that are the focus of what one is talking about in things like the mentaculus. Okay, it's supposed to be a worldly thing, not an epistemic matter.
Mm-hmm. And right, I agree with you. And I think that we're all pretty familiar with the subjective or epistemic kind of chance. In the classical picture, I mean, there's going to be a determinate outcome to a coin toss, but we give any given toss a 50% chance of landing heads or tails because we just don't know but what that outcome will be. But where might objective probabilities or chances come from, if not in this classical picture?
Well, let's see. I'm not sure. Maybe we should back up a little. First of all, what you just said about the coin toss, which is we don't know what the outcome is going to be, but it's going to have a determinate outcome. That's true even in a theory whose dynamics is chancy. Okay. It's going to have a determinate outcome. At the end of the day, it's either going to land heads or tails. So it isn't the determinateness of the outcome that distinguishes, say, theories with a chancy dynamics from theories with a non-chancy dynamics. It's a deterministic relation between the way things start out and the outcome that's present in theories with a deterministic dynamics and absent in theories with a chancy dynamics. But our thought was that if you have this sort of Humean, Lewisian picture of laws in your head, okay, if you have this picture of laws in your head where laws are not, metaphysically speaking, worldly things, they're concise. They're certain kinds of summaries that jointly maximize concision and informativeness of the sort of distribution of physical properties over the four dimensions of space-time. If you're thinking of laws that way, then there's no reason why there can't be a genuinely chancy law about initial conditions, okay? Because such a law might well be a part of a maximally concise and informative set of propositions that one puts forward in order to try to summarize this so-called Humean mosaic, okay? This distribution of physical properties over the four-dimensional manifold that is the history of the universe. So the idea is, all you're doing when you talk about dynamically chancy laws is trying to say as concisely as you can and as informatively as you can something about how the history of the world goes. The same thing would be true of a dynamically chancy law, of a genuinely physically chancy law, but not dynamically chancy law, governing initial conditions. That is, people sometimes are puzzled when one talks about an objective chance distribution over possible initial conditions of the universe. People will often say, I don't understand. The universe has only one actual initial condition. What can talk about objective chances of different possible initial conditions possibly mean? In the context of this kind of Humean picture of law that Barry was talking about, it means something like this. I have this story that I like to tell about how to understand a Humean account of laws in general. This story about, you get an appointment with God, you go to his office, you get all dressed up, you go to his office, it's a very big day for you, you're shown into the office, and God says, what would you like to know? And you said, like to know about the world. And God says, great. And God starts reciting the facts of the Humean mosaic. He says there was an elementary particle of such and such a kind at such and such a point at such and such a time. And there was an electric field of such and such an intensity at such and such a point and such a time. And he's reeling off this infinite list of particular facts about the world. This list of particular facts is what I'm referring to when I talk about the Humean mosaic. And you're listening to this recitation of all these particular facts. And it dawns on you pretty quickly that this is not at all what you want, that this is not the kind of thing that you could possibly hold in your head or that would be of any use to you. And besides which, you're supposed to get a haircut later in the afternoon and so on and so forth. And you need God to speed this up in one way or another. So you say to God, look, it's beginning to dawn on me that this is not what I want. I want something else. God says, what do you want? You asked me to tell you about the world. I'm telling you about the world. You say to God, "You're right. I take it back. Here's what I'd like." And for this illustration, Barry's T-shirt is particularly appropriate. You say, "Here's what I think I'd like. Tell me as much as you can about the world, subject to the constraint that I could print it all on a T-shirt." Okay. And God says, "Okay, good. That is, tell me something which jointly maximizes concision and informativeness. Tell me all you can, subject to the constraint that the entirety of what you tell me could be printed on a T-shirt." So God says, "Fine." And God says, and God will, for example, say, "Here's something that should be on the T-shirt, F equals ma. Here's something else that should be on the T-shirt." I mean, we're talking about a classical world here. Newton's law of gravitation and Coulomb's laws of electrostatic attraction and repulsion and Maxwell's equations of the electromagnetic field. And you say, "Okay, that's great, but there's a lot that's not telling me." There are ways for the world to behave that are consistent with the laws we've written down so far, with the dynamical laws that we've written down so far, that we know the world doesn't behave, okay? For example, the time reverse. These laws have this property of being time reversal symmetric. These dynamical laws have the mathematical property that for any process which is in accord with those laws, the exact same process going backwards will also be in accord with those laws. But there are all kinds of things that whose backward evolutions never happen. I see stones falling into ponds and circular ripples going outward. I never see circular ripples coming inward on the surface and then a stone being ejected out of the pond. I never see smoke collecting from all corners of a room and going back into a cigarette, so on and so forth. I never see heat spontaneously transferred from a cooler body to a hotter body, so on and so forth. And yet, all of these are solutions to the various equations that we've put on our T-shirt so far, F equals ma together with the force laws and so on. Isn't there something more you can tell me? And God says, "Well, that would have to be something about initial conditions. I could tell you the initial condition, but that would take up a precise description of the initial position and velocity of every particle in the universe."
Your whole wardrobe.
Right. And that wouldn't fit on the T-shirt, and it wouldn't fit, as Barry says, on a whole wardrobe. So God says, "What are we going to do here?" God says, "I know. I'll tell you something about the initial condition. There's indeed only one initial condition, but here's a simple way to tell you something, although not everything about it. It's one of those initial conditions which is typical with respect to a probability distribution like this, okay? If you go with that, then you won't go around in the world expecting stones to leap out of ponds. You'll assign a very low probability to that. You won't expect smoke to collect from the corners of a room back into a cigarette. You won't expect spontaneous transfers of heat from a cooler body to a hotter body, so on and so forth. So these kinds of probability distributions are exactly like the dynamical laws, F equals ma, so on and so forth. Simple things that I can tell you, appropriate parts of a maximally concise and informative set of propositions about the way the world is, that are concise to the degree that you could fit them on a T-shirt. This is how chances over things like initial conditions, even though there's only one initial condition, might enter into such a description, might find their way onto such a T-shirt. That qualifies them on a Humean view, on a Lewisian view, on a Loewerian view, as probabilistic laws in exactly the same way that dynamically chancy laws are probabilistic laws.
Can I add a few things? Robinson, you may have a question first, or about
No, go ahead.
Okay, there are a couple of things. I love David's story and his way of telling it. I would say that, of course, if Hume heard that it's being expounded by his having an interview with God, Hume would turn over in his grave or wherever he happens to be right now. The other thing is that the part of the Humean account that's being used here is not one of the things that comes to people's minds at first, and which David Lewis also is part of his account, which is that there are no necessary connections among events. That's not what's being employed here. The thing that's being employed here is that what laws and what probabilities do is they systematize and summarize, as David was saying. And if you understand that this is what the job of probability is, you could see how probability was introduced by, let's say, people noticed that there were certain sequences of events which look like they kind of have a regularity, but you can't say what will happen next. But you look at sequences of them like coin flips, H, H, T, 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 H, T, H, T, H, T, T, and you realize, or might realize, that we could systematize or summarize that by saying that the probability of individual outcomes is, let's say, a half, and the outcomes are independent of each other. That gives you a lot of information, particularly if the information is extracted via this thing that Lewis called, and I mentioned earlier, the principal, by telling you what your degree of belief should be. And that's what probability is. And for my own part, I got into philosophy because I was a pain in the neck to my physics and my statistics teacher. I also had a history teacher too, asking them, what are you talking about when you're talking about probability all the time? And they said, go to the philosophy department, which I did. And they said, well, we can tell you what to read, but you may have to spend time doing that. And I was personally very satisfied, happy when I ran, of course, Lewis's account. And then I spent a lot of my time sort of developing Lewis's insight beyond what Lewis had to say about it. And there are ways to do it, but it does require a kind of reorientation about metaphysics because it conflicts, as David was saying. People have this idea, Popper, for example, thought, if the world is deterministic, there can't be any objective probabilities. But this is a way in which the fundamental dynamical laws might be deterministic, but there are objective probabilities as well. And I think also this is connected to a certain view about time. If people think that the way the universe is such that the laws take the state of the universe and evolves it over time, and time, very differently from space, is doing something. It's passing, going, evolving. There's a growing block or something like that, or a presentist view about time. Then this Lewisian conception about laws and probabilities won't make any sense. So I think it involves rejecting this kind of view. And the interesting thing is, as I'm sure we'll get into in a minute, is the Mentaculus shows that you can actually provide explanations for why it is that time has features that it has, why it is that we can influence the future but not the past, why we, as David was saying, we don't see smoke recollecting into cigarettes. We see it passing cigarettes, but we don't see people smoking very much anymore, at least not tobacco. And so what metaphysicians thought they could explain, and their explanations were horrible, to be frank, that's another podcast, what's wrong with presentism and growing block accounts and so on. But those are not scientific explanations at all. But what they wanted to do could actually be captured within this kind of framework that David and I are talking about. So that's what I wanted to add to with David's very nice way of putting.
That's all great. I talked to another JBI fellow, Lee Smolin, and he's a very ardent presentist. So that was interesting. But David, thanks for...
At that moment he was. I'm not sure now.
Good one. Okay, David, thank you for clarifying my terminological conflation of determined and determinate. I think that was really crucial. And Barry, I would like to come back to times arrows, definitely. But one thing that I think might be helpful to do before all of this is, I know from talks with you from when you visited Stanford and we got middling pizza and then you gave your talk, but I know that there are three basic components to the Mentaculus, and I have in mind the dynamical laws, and then David's past hypothesis, and the probabilistic laws. And I'm wondering if maybe we should just lay out these three components first before we move on. And
yeah, there's also so how many components there are is going to depend on the nature of the dynamical laws,
the size of the t-shirt.
And right, in something like classical statistical mechanics, where you're taking it for granted that the dynamical laws of motion are deterministic, there are going to be these three components. First of all, there's going to be the exact microscopic deterministic dynamical laws of motion. Then there is going to be some kind of principle of the form, other things being equal, the uniform distribution over microstates. That is, in the absence of other information, you should assign a uniform probability over the space of microstates compatible with everything else.
Not because of ignorance.
Right. This is a law. Right. This is, maybe it's worth saying, people will often say when you talk about these probability distributions over initial conditions, but these aren't worldly laws. This is just a way of making up for your ignorance. Maybe it's worth pointing out that from a Humean standpoint, that's what all laws are. That's what dynamical laws are too, okay? There's a fact of the matter about what's going to happen in the future, okay? And somebody with infinite cognitive capacities, somebody like a god, would have no use for dynamical laws, would have no more use for dynamical laws than for probability distributions over initial conditions. These are things that the humans want on their t-shirts. These are mnemonics or helpful, concise descriptions of what's going on. But somebody who has available to them, the storage, the mental storage capacity to hold in mind all of the facts about the history of the world has no use for laws of any kind, not dynamical laws, not non-dynamical laws. None of those are worldly things. The worldly thing is the mosaic. The worldly thing is the total list of facts, okay, of particular facts about what's going on at particular points in space-time. And that's it. Okay. So what Barry says about this not being about ignorance is exactly right. That is, it's no more about ignorance than any other laws are. Okay. It's exactly as objective as any other claims about what the laws of nature are. Good. So you have you have a law like, among any n reproductions of the same state of the world, of the same macro state of the world, or of any n occasions where the state of the world falls within certain parameters, the frequency with which you'll be getting exactly this microstate or exactly that microstate will be such and such. These are objective claims about the actual structure of the history of the world. Good. So, as I was saying, in the case of something like classical statistical mechanics, you'll have these three components: the microscopic deterministic equations of motion, this statistical postulate, which is what we've just been talking about, and then a further constraint to the effect that the initial macro state of the universe is constrained to be that state that we're closing in on by means of doing cosmology, some highly condensed, hot, very low entropy state of the universe. Okay, and the point is, in something like classical statistical mechanics, once you've put those three in place, as Barry was just saying, these turn out not to be agnostic, not to be jointly agnostic about anything. Okay. Once those three things are in place, you have a probability assignment, a precise probability assignment to every formulable proposition about the physical history of the world. Good. In a different theory, in certain versions of quantum mechanics, like the GRW theory, for example, where the laws themselves, the dynamical laws themselves are chancy. It turns out that in the context of something like the GRW theory, you probably won't need the statistical postulate. The dynamical chances in the theory itself will end up doing the job that the statistical postulate does for you in the context of classical statistical mechanics. So in a case like the GRW theory, the Mentaculus has only two fundamental principles: this principle about constraining the initial macro state, and the microscopic dynamical laws, which are themselves chancy. So the number of separate, logical postulates that you're going to need to build up the Mentaculus will vary between something like classical mechanics and something like the dynamics of the GRW theory. That's one of the exciting things about a version of quantum mechanics like the GRW theory. If something like the GRW theory is true, you would be able to trace all of the objective physical chances in the world back down to these quantum mechanical chances of the kind you get in the GRW theory. If, on the other hand, you're starting with a theory whose microdynamics is deterministic, like classical mechanics, like Bohm's theory, so on, then you're going to need then you're going to need a statistical postulate in statistical mechanics, and in Bohm's theory, you're going to need an additional statistical postulate in order to get the quantum mechanical chances to come out right.
Well, first, Barry, could you show your whole T-shirt?
Yeah, you can't see it. I'm not sure how my iPad is showing me. Visible now?
That's, yes.
Okay. Well, on the T-shirt in the middle is a depiction of the history of the world. The thin lines represent possible micro-histories of the world. The thicker cylinders represent possible macro histories of the world, where macro means description of the world in terms of our ordinary macroscopic languages, particularly language of thermodynamics, but all other macroscopic ways of describing the world. Remembering that the way we macroscopically describe the world can be realized or made true by an enormous number, infinitely many really, possible microscopic states of the world and microscopic histories of the world.
Could you give an example of that? I don't think it's a really intuitive.
Sure, of course. Take, for example, from classical thermodynamics, that a gas of a certain volume and density might have a certain temperature. That temperature is the average kinetic energy of the molecules in that gas. But there are lots and lots of different ways in which those molecules might be moving around, which give exactly the same average kinetic energy. They all result in the same macroscopic condition, but there are infinitely many microscopic states which realize functionalists like to use that word, or in philosophy of mind, realize, make true the macroscopic state. So the really interesting point, and the really interesting point for philosophy, is that on this picture, the Mentaculus picture, while the world may be evolving deterministically at the fundamental microscopic level, it's evolving indeterministically at the macroscopic level. So these macroscopic descriptions of the world, if you describe the macroscopic state of my room or the earth or whatever, now describe the macroscopic state of the solar system now in great detail, macroscopically, there'll be a certain probability given that of, let's say, a female president being elected in 2032, president of the United States being elected in 2032. Many people find that incredible, but that's a consequence of the Mentaculus. That's what David is talking about, this account not being agnostic about anything.
Or imagine a simpler case like this. You have a pinball, making its way down, okay? And it lands on a certain pin. More or less macroscopically by eyeballing it, it's landing, the center of its bottom surface is landing square on the pin, okay? If we were given an exact microscopic description of the position and velocity of every one of the elementary particles making up the ball itself and the pin it's landing on, and so on and so forth, we would know for certain. We could, in principle, predict for certain whether the ball is going to fall off that pin to the left or to the right. So on a microscopic level, we've got a completely deterministic evolution. But on a macroscopic level, I don't know what, it's a good characterization of our experience that interactions like that are chancy, okay? That there's a 50% chance that the ball will fall off to the left side of the pin and a 50% chance that the ball will fall off to the right side of the pin. So you can have these completely deterministic evolutions that are completely deterministic on the micro level, okay? And which, when you combine them with this probability distribution over initial conditions that we were talking about, yield robust and reliable chancy laws about macroevolution. Okay, and they'll be robust and reliable in the sense that if you do this with 1,000 pinball machines and you drop 100 balls into each one of these 1,000 pinball machines, you're going to get this nice Gaussian distribution at the bottom. Okay, that's what you get from there being an equal chance that the ball falls off any given one of these pins toward the right or toward the left. Okay, so there's a real sense in which you have robust macroscopic patterns that testify to chancy macroscopic dynamical evolutions, even though what you have on the micro level is a perfectly deterministic microevolution. And the link between this deterministic microevolution and this chancy macroevolution is this chance distribution over initial micro conditions compatible with the initial macro condition.
So, Robinson, since you may get some fancy philosophers of physics watching your podcast, I'm sure you will, we should just give a nod in the direction of course, there are issues about the classical mechanical laws being completely deterministic that have been well, discussed in the literature. And there are other finer points here. But what David is saying is, of course, if something people should want to agree with as a big picture account of what's going on.
Well, just briefly, or maybe not briefly, before we move on to some of the the many applications of the Mentaculus. I'm wondering if the three of you think, or the two of you, there are three of us because Barry
There's
has
four of us.
two.
There's a cat also.
Yes. If there are any other basic components of the Mentaculus that you think we ought to spend a little more time on, or if you think it's totally.
I just wanted to say one thing.
Mhm.
These three components are the components that David just went through. There are some issues about them. One issue we discussed is exactly what is the metaphysical or ontological status of the probability distribution. Another is what is the actual status of the past hypothesis. David was saying that both of these should be considered as Humean laws. I was adding that the word Humean there should be understood in the idea that they are systematizing, not and disconnected from Hume's rejection of necessary connections. That's another issue which we could put aside for the moment. And maybe I could just take this time to just advertise that I have a book coming out in the spring called What Breathes Fire into the Equations, which spells out the background and a bit about the application of this probability distribution, and another book that'll come out later called The Mentaculus Vision, which will be about, applications of the Mentaculus to things we're just about to talk about. So we got the three ingredients down pat. We haven't discussed all the issues that might come up about them. There are some fine points about how you want to think about the what fit is for the probability distribution, and there's a bit of a literature making objections and replies, and some alternative views and so on. But I'll let you bring up the objections later.
Okay. Well, since you mentioned earlier the direction of time and time's arrows, but I held off on that for a moment. Maybe that's where we should get started when we talk about the application. So what does the Mentaculus have to do with time's arrows?
Here's a way of describing sort of a path towards this general idea of this sort of architecture of our fundamental physical account of the world, which is what this Mentaculus stuff is supposed to be. You start off you start off with things like the Boltzmannian account of a bit over 100 years ago, of the relationship between classical mechanics and thermodynamics. Okay, you have this idea that that things like gases are really large collections of particles, and those particles, if Newtonian mechanics is the fundamental law of the motions of material particles, those particles are obeying Newtonian mechanics. Those particles are bouncing around and smacking into one another in accord with the laws of Newtonian mechanics, and there should be some kind of account of the way large numbers of particles are going to smack into each other and bounce around in accord with the laws of Newtonian mechanics, that are from which somehow a description of the familiar properties of gases, the behaviors of pressures and temperatures and volumes and densities and so on and so forth, is going to emerge. Okay. And Boltzmann's big idea is that Boltzmann's huge achievement is to begin to make it plausible that the following is true. Okay. You take, like Barry was saying before, a typical macroscopic level description of an object like a gas. Okay, you have this large collection of particles in a box, and the boxes, the stuff in the box is characterized by these macroscopic variables like temperature and pressure and density and volume and so on. It ought to be intuitively clear that corresponding to a macro description like that, there will be many, 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 indeed an infinite number of, as it were, compatible micro descriptions of the individual subatomic particles that make that gas up, okay? Small variations in the positions and the velocities of some small subset of those particles is not going to alter the overall macroscopic description. There will be many, many microscopically distinct ways of realizing a single macroscopic description of a gas like that. And Boltzmann has this idea that you can show that on some sort of sensible definition of most or of the vast majority of the microstates compatible with a macrostate like that, okay, if you evolve them forward in time using the Newtonian laws, are going to give you the kinds of evolutions on the macro level that you're used to from your everyday thermodynamic experience. So, for example, if you have a macrostate which consists of a cooler body and a hotter body in thermal contact with one another, you look at all of the infinity of microstates compatible with a macro description like that, okay? And there'll be a sense of most, a sensible sense of most, given that the macrostates are infinite. That may seem counterintuitive, but there are these measure theoretic senses of most, okay, in which the vast majority of the microstates compatible with that macro description, a hotter body and a cooler body in contact with one another, okay? If you evolve them forwards in time using Newton's equations of motion, are going to take you in the direction of those two temperatures tending to equilibrate with one another rather than to get farther apart. Okay, they'll take you in the direction of heat flowing from the hotter body to the cooler body rather than from the cooler body to the hotter body. And all of the Boltzmannian arguments are designed to make it plausible that in every simple thermodynamic case, something like that is going to be true. Okay. The entropy will statistically tend to increase, so on and so forth, where you're equating the relative populations of microstates that will do this and microstates that will do that macroscopically with the probability of the system doing this or the system doing that macroscopically. Well, is that clear so far? Good. So the idea is you can explain thermodynamic behavior. That is, Boltzmann makes it plausible that you can explain thermodynamic behavior. It ought to be mentioned that none of these results is fully general or fully rigorous mathematically, nowhere near it. The bottom line here is that we can't do these calculations. There are too many particles involved. We'll never be able to do these calculations exactly. No envisionable computer will ever be able to do these calculations exactly. They're just way, they involve way too much data.
Not even a quantum computer.
No envisionable computer is going to be able to do this. But Boltzmann has these very nice arguments which make it plausible initially that claims like the one I just made are true, okay? That the vast majority of the microstates compatible with a given thermodynamic macrostate of cold body here, warm body here, are going to lead, when you plug those initial microstates into the Newtonian equations of motion, to states where the temperatures equilibrate exactly in the way we see them doing in our everyday macroscopic lives. Good. This result is very impressive to people. Okay, this begins to suggest a way of drawing connections much more generally between physics and the special sciences. Okay, science is not only like thermodynamics, but biology and economics and I don't know what. That there's a general model here for analyzing the connection between fundamental physics and the special sciences. And the general model is going to involve adding to the dynamical equations of motion, the deterministic dynamical equations of motion, some kind of postulate about probability distributions over initial conditions in the way that Boltzmann did. Moreover, Boltzmann recognized that if you were to do your calculations about the future and the past just by taking the present macrostate of the world, okay, putting this uniform probability distribution over all the microstates of the world compatible with the present macrostate of the world, plugging those into Newton's equations of motion and calculating backwards and forwards, it would give you the wrong answer. Okay, it would give you good answers about the future. The entropy is rising, temperatures are equilibrating, things are wearing down, so on and so forth. But it would give you the exact same answer towards the past. In the past, things would be more worn down. I would look older than I do now, imagining that such things are possible. Paper would be yellower
like me.
in the past than it was now, so on and so forth. It gives you the wrong answer about the past. Boltzmann realized this as well. And so it looks as if in order to make this whole system consistent internally, both internally consistent with itself and consistent with our everyday macroscopic experience of the world and our everyday experience of the difference between the way the past looks and the way the future looks, you're going to need to add yet another postulate about the initial macrostate of the world. This is the postulate that Barry and I call the past hypothesis, the third component of the Mentaculus. Boltzmann realizes if you add that, you've got yourself a good account of thermodynamics. Good. What's interesting is you play around with that for a bit. This addition of the past hypothesis, if you play around with it, if you draw out its consequences, in the appropriate way, it turns out is not only going to give you an argument for the asymmetry between past and future that you find in thermodynamics. That is, as you go toward the future, temperatures tend to equilibrate. As you go towards the past, temperatures tend to disequilibrate. As you go toward the future, entropy rises. As you go toward the past, entropy gets lower. That's the thermodynamic time asymmetry. If you play around with this exact same past hypothesis, that's the one you find you need in order to underwrite the thermodynamic time asymmetry, you can make very impressive plausibility arguments that this same hypothesis about the macro condition of the world in the distant past at the beginning of the universe is also going to be able to underwrite what look on the surface like very different kinds of time asymmetry that we encounter in our everyday lives. For example, the fact that we have a very different kind of epistemic access to the past than the kind of epistemic access we have to the future. Okay, if I want to know what I'm going to have for breakfast tomorrow, that's a very complicated calculation I have to do that involves most of the elementary particles in the universe, or at least within my light cone, so on and so forth. If I want to know what I had for breakfast yesterday, it's the easiest thing in the world. Nobody needs any training in physics in order to do that. You simply remember, okay, what you had, or you look on the security camera video where you were eating, or something like that. We have a wildly different kind of epistemic access to the past than we do towards the future. It turns out, or at least I think it can be made very plausible, that this exact same past hypothesis that Boltzmann found necessary in order to explain the thermodynamic asymmetry will also explain the temporal asymmetry and epistemic access, will also explain the very different kind of the difference between the very different kind of epistemic access we have toward the future and toward the past. Moreover, there's a third kind of there's a third kind of temporal asymmetry, which we're running into all the time in our lives, what you might call a causal asymmetry, or an asymmetry of intervention, or an asymmetry of influence. We find that by acting now, and this is the very foundation of everything we think about ourselves as agents, and so on, we find that by acting now, we can influence the future, whatever exactly that means, in a way that we can't influence the past. Our capacity to influence things, our capacity to control things, also has in it a very profound time asymmetry, a time asymmetry which, like the thermodynamic asymmetry and like the epistemic asymmetry, is something enormously mysterious if the only part of physics you're looking at are the dynamical equations of motion. Because those dynamical equations of motion don't make any distinction between future and past whatsoever. They have this strict, precise, pure mathematical property of invariance under time reversal. Okay, so if you look at these asymmetries, all three of them, from the standpoint of the microscopic equations of motion, all three of them are profoundly mysterious. It's hard to see where all three of them could come from, because there's no way to even get a foothold on this from the standpoint of the microscopic dynamical equations of motion. They make no past-future distinctions at all. Boltzmann finds that by adding the statistical postulate and by adding the past hypothesis, he can take care of the thermodynamic time asymmetry, or he can plausibly take care of the thermodynamic time asymmetry. Other people find, since Boltzmann, that this same past hypothesis looks like it can also take care of the epistemic time asymmetry and of the causal time asymmetry. And you suddenly begin to get flushed with success, okay, and flushed with a sense of power, and you say, maybe this can take care of everything. Okay, maybe just these three components give you a complete probability map of the world. Okay, that's the sort of intellectual genesis of this idea. That's the route towards this idea. It very much depends on attempts to get to the bottom of these time asymmetries. So thinking hard about these time asymmetries and about what you would need to add just to the dynamical equations of motion in order to explain these time asymmetries is how you build this architecture in the first place. Once you have it, it begins to look plausible for all kinds of reasons that this is all you need to explain nature. Okay. Of course, when we talk about the dynamical equations of motion, we can talk about the specific example of the Newtonian dynamical equations of motion. We know those are false. We could also talk about the non-relativistic quantum mechanical dynamical equations of motion. We know those are false. We could talk about the relativistic field theoretic dynamical equations of motion. We're pretty sure, because of gravitation and because of problems with renormalization, that those are false. So we don't know yet what the true microscopic dynamical equations of motion are. That's a slot in this architectural structure that remains to be filled in, maybe by string theory or by brain theory, or I don't know what. Similarly, once we have the basic ontology of the world, when we know the exact microscopic dynamical equations of motion, and if we know they refer, say, to strings, that's going to lead to a more precise formulation of the statistical postulate and the past hypothesis in terms of those languages. So this is at the moment just a sort of a broad architectural structure with various slots in it, okay, in which you're supposed to place things that are yet to be discovered about the fundamental structure of physics. But when you're playing around with this, you're trying to make a plausible case that it looks like a general structure like that is going to be all we need. Sorry for talking so long.
Yeah. Well, it was great, David. I have a few points. Can I make, Robinson, unless you want to?
No, absolutely.
David?
Go ahead.
Okay. So let's see, in order. One is the point that David was making towards the end about the fact that we don't know the ontology of the world exactly, but we do know how to describe the world macroscopically pretty well. It can be improved upon there too. We don't know what the dynamical equations are and so on. But as Sean Carroll points out, that pretty much any successor theory at the micro level has got to agree with respect to the macroscopic world with what, basically quantum mechanical, quantum field theory says about the world. It's only in very special circumstances that these theories run into trouble, that we don't, usually not in such circumstances, unless you visit black holes from time to time. The other point I wanted to make was when you're talking about the past hypothesis. So that's a name that David gave. It's a very good name, but I think it's also a little bit misleading in this respect. Of course, it's a hypothesis, but it's also a law. Furthermore, calling it the past hypothesis has led some people to think that the view imagines already supposing a distinction between past and future. But that's not true. Rather, it earns its name as the past hypothesis by doing all the work that David just described.
Yeah, that's an important point. Yeah.
And the last thing I wanted to say this, I started off being a philosopher. We didn't get into this. David started being a physicist. So he doesn't have the same background in philosophy with the same sort of worries about philosophers, the same interactions with philosophers that I have. But, the epistemologists are all around me. Action theorists are all around me. David's time and chance makes the most important contribution a more important contribution to epistemology, for the reasons he said, by explaining the epistemic asymmetry, and to action theory by explaining the asymmetry of influence, than pretty much any other discussions in these areas. I don't mean to make a competition, but it should be something that's on the philosophers' reading list so that they understand what's going on. They just sort of, in general, it's just sort of presupposed, or it's not even a question that's asked in epistemology. I'm not sure if epistemologists ever really bothered to ask the question why there's this epistemic asymmetry, except they sort of thought there's a causal asymmetry that must be responsible for it, or something like that. But the Mentaculus explains all that. The last thing I wanted to say is this. When David was glowing, waxing, very poetic, and saying, now you look like I have a whole theory of the world, I then remembered the movie, and meant I should have said earlier that the person who gave it this name, the Mentaculus, in the movie, is clearly out of his mind. Okay, but we mean this seriously, to be taken a serious proposal about the world, serious enough to be, criticized, and there are criticisms of the whole story, but I think it is very serious and very, very, very exciting to me, at least, as a comprehensive view of the world. That's a kind of, a theory of everything that's also operates at the macroscopic level as well.
Just to expand a little bit on what Barry just said, there is a big obstacle to teaching this stuff and a big obstacle to communicating it successfully to other areas of philosophy, traditional epistemology, traditional action theory, so on and so forth, is getting people in a mood where these time asymmetries even arise as a question. Okay, it's not immediately easy to see why it isn't analytic, as it were, that memories are memories of the past. Okay, that of course we have a different kind of epistemic relationship to the past than we do to the future because it's the past. Okay. And of course, we have a different kind of relationship vis-a-vis capacity to control or influence the future than we do to the past, because the past is done, because the past is finished, because the past is locked in. Okay. And the idea that none of those notions of being done, of being locked in, of being the past are there to be found in the fundamental equations at all, okay? And you have to really focus on that to get yourself to feel that there's a question to be addressed here at all. The harder part is not answering the question, it's asking the question in a clear way. It's so baked in that it's hard, that these things are somehow analytic to what you mean by past, or analytic to what you mean by memory, or analytic to what you mean by control or influence. And the mood you have to get yourself in, okay, is like, this is what I always tell students. You have to imagine that you suddenly discovered that you have a very different kind of epistemic access to things to your right than you do to things to your left, okay? Or you find that by waving your arms around here, you can have profound influence on things to your right, and you have no influence at all on things to your left. Okay, if it occurred in that way, that spatial way, rather than a temporal way, it would be obvious to everyone that there's a question to answer here. Why? What's going on? What's the asymmetry here? What's preventing this influence from propagating to the right just as it propagates to the left? What is it that's preventing me from getting information from the right just as I get information from the left? If you sort of focus on that, it'll become obvious, number one, that there's a question here, and number two, that this is a question to which physics, not pure philosophical reflection, ought to be, to which we ought to turn to physics to answer, and to which physics owes us an answer.
Mm-hmm. That's great.
That's my little sermon about that.
That's great, and a beautiful way of making it very, very vivid. But philosophers thought that metaphysics was going to answer this kind of question. But
nobody would think that metaphysics is going to answer the kind of question I just described.
Absolutely. That's why it's so nice way to put it, in such a vivid way to put it. So philosophers have now given lip service ever since Quine. You're not supposed to think that meaning is going to answer the question, as you were suggesting, since Quine you know, we were supposed to naturalize metaphysics, but take that seriously. That means, as Dave was saying, physics should answer this kind of question, not by having some sort of metaphysical view about time, which somehow makes it the case that the past is different because it's a different status in reality or existence, or something like that. And I'm sorry to hear that Lee Smolin. I don't know if Lee Smolin thinks about these kind of questions like that, but I don't know whether he thinks presentism could help with any of these at all.
No, Lee definitely has a very different view about this. Lee wants to find a place in fundamental physics for passage and flow, and yet Lee is working from a very, very different set.
So how does the presentist metaphysics
initial presumptions? What'd you say, Barry?
Well, Robertson said, and I knew this before from Lee, that he's a presentist about time. So are you saying that he's not going to appeal to that to explain any of this phenomena? That would be a reasonable thing to do. And I wonder, why is he a presentist?
No. He is going to appeal. No, he's going to think. I don't want to speak for Lee. And I'm not sure I understand the view so well. What I do know about Lee is that he wants to find a place in fundamental physics, okay? This is not something, in a picture like ours, all the talk about flow, all the talk about passage, so on and so forth, this is going to be analyzed. We're going to give an analysis of this in terms of these various asymmetries, epistemic, causal, so on and so forth, the buildup of memories as time goes on, so on and so forth. And those are in turn going to be explained in terms of the three fundamental physical postulates of the Mentaculus. And so at a fundamental physical level, these words like flow and passage aren't going to appear anywhere. What I know of Lee's view, and I don't want to say more about it than I do know, is that he's looking for a view on which these notions of fundamental, these notions of passage and flow and so on are somehow absolutely fundamental to our physical description of the world. And that's going to be a very, very different picture than the kind we're presenting.
I wonder how presentism works there, but let's leave that for another occasion. I just want to say this, whenever this bit about time comes up, what comes to my mind is a poem that some of you may know, called The Paradox of Time by some guy named Arthur Dobson, I think is his name, or Henry Austin Dobson. It has the line in it, "Time goes, you say, alas, time stays, we go." I like that a lot because the Mentaculus picture is one of a block universe. There are events that occur spread out to a block universe. So we are going in the sense that we occupy different locations in the block universe at different times, but time isn't going anywhere. Time isn't passing.
I'm not sure exactly in what sense it's true that we occupy different locations at different times. We occupy a certain worm in.
Yeah, that's all I mean.
That's what
I don't mean anything
we
different
occupy
from
that
that.
timelessly.
I didn't mean that we are something over and above the worm.
Okay.
You and I are both worms, or anyway, we'll be eaten.
or lower, right?
Well, there are a lot of things to say. I'll restrict myself to two of them for the moment. And one, that was very high praise you gave earlier for time and chance. So hopefully our philosopher listeners will pick it up. But David, you gave a great synopsis of three important arrows. So the epistemic arrow, the thermodynamic arrow and the causal arrow, but there's one other arrow that I wanted to ask about. So granted, Barry, as you put it, we don't know the fundamental ontology of the world yet. And in David's vernacular, this is a big slot that needs to be filled. And the quantum theories aren't complete. But the arrow that I wanted to ask about was wave function collapse. And even you also mentioned Sean Carroll. So even many worlds advocates, even if they don't believe that the wave function collapses, there's still a temporal asymmetry here. And I'm wondering how or if the Mentaculus has anything to say about this sort of quantum era.
Yeah, sure. First thing to say is if there's such a thing as physical wave function collapse, say as in the GRW theory or something like that, then the Mentaculus has a slightly different structure. Then you won't need then you won't need a statistical postulate. You'll just need the dynamics, which has chances in it already, and the past hypothesis. You might think that so there are two interesting features to point out about the collapse of the wave function in something like the GRW theory. One is it involves dynamical chances. The other is the law is not time reversal symmetric, like the laws. Yeah.
Yeah, I was just going to say, I don't think that all of our listeners know the GRW, Rimini-Weber theory. So maybe just like in a minute, you could say what it is.
There is a problem at the foundations of quantum mechanics. I would say, this reminds me, if I can just digress for a second.
Please digress.
I had to talk to my son's sixth grade class many years ago now. And as I walked in, I was going to talk about actually some things about time, which I thought the kids would be excited about, maybe time travel or something like that. And as I walked in without any warning, the sixth grade teacher took me aside and said, you know what, if you could begin with just a 5-minute little summary of what philosophy is, that would be great. Okay, that's something comparable to what you've just asked me to do in 5 minutes about the GRW theory. It actually went okay. I won't say what I said, but anyway, there is a puzzle at the foundations of quantum mechanics called the measurement problem, which I and most students of the foundations of quantum mechanics regard as the sort of central problem at the foundations of quantum mechanics, which is that quantum mechanics, as it's standardly formulated, gives us probabilities of how a given experiment on a given precise macro state of the world is going to come out, okay? The trouble is, so it gives us a certain probability associated with the outcome of the measurement being A, and a certain probability associated with the outcome of the measurement being B, and a certain probability associated with the outcome of the measurement being C. The trouble is that I don't know how to put it. Quantum mechanics, as it's usually formulated, is profoundly opaque about how it is that one or the other of these outcomes actually manages to manifest itself in the world. The standard quantum mechanical picture gives us a superposition of these three outcomes. And if you just apply the fundamental quantum mechanical equations of motion to the measurement process, what those equations of motion are going to tell you is that you're going to get a result which is a superposition of the measurement having come out A and the measurement having come out B and the measurement having come out C. That's, of course, not what happens when we do it in the laboratory. God knows what that would even look like. Okay. Our experience is we either get A and we get that a certain percentage of the time, or we get B and we get that a certain percentage of the time, or we get C. And the basic equations of motion of quantum mechanics don't give us any hint of, as it were, how that transition from three possibilities to one actuality takes place. Okay. And in order to give a coherent picture of that, various solutions to the so-called measurement problem have been proposed. One of those solutions is that every now and then, the wave function, for an instant, stops evolving in accord with these fundamental equations of motion and involves instead in a chancy way, which in these sorts of circumstances will produce either A or B or C with the appropriate probabilities. Okay. And the way you have to modify the equations of motion in order to get a theory like this involves introducing into the theory two elements that weren't there before. One, genuine chanciness, because the Schrödinger equation, which is the fundamental dynamical equation of quantum mechanics, is completely deterministic. It, in a deterministic way, gives you this superposition of three outcomes, which you don't know what to do with. Good. So getting one or the other of these outcomes to emerge, using this particular strategy, this strategy of so-called the collapse of the wave function, is going to involve modifying the fundamental equations of motion in ways that involve introducing both genuine physical chances and time reversal asymmetries, neither of which are present in the Schrödinger equation. Good. So you might think that in particular, these time reversal asymmetries that you have to introduce might, in addition to solving this measurement problem in quantum mechanics, be what lies at the bottom of all these time asymmetries: the thermodynamic time asymmetry, the epistemic time asymmetry, the causal time asymmetry. It is, after all, now an asymmetry, a time asymmetry in the fundamental dynamical laws of the world. It turns out, if you do the analysis, that although the chanciness may be able to take over the full job of the statistical postulate, okay, in the earlier version of the Mentaculus, the time asymmetry involved in the collapse is not going to be able to take over the full job of the past hypothesis. You're still going to need a past hypothesis in order to account for the thermodynamic and epistemic and causal differences between the past and the future, even in the context of this kind of chancy and non-time reversal symmetric theory of the collapse of the wave function. Okay, so it turns out, I don't know if that's enough of an introduction. If you want to ask me a question to clarify it further, by all means, jump in.
David, make it clear that the metaphysics, the Humean metaphysics, is an orthogonal issue.
Yes.
Yes,
absolutely.
Theory is
These chances, metaphysically speaking, are just like the probability distributions over initial conditions. Yeah, thank you, Barry.
And within the Everett account, which I know that Robinson has got podcasts about, they have a real problem, as you've pointed out in many articles or discussions with what to say about probability. And then you have to have a whole other different kind of story about probability.
Right. But so anyway, In the GRW, if you were to adopt a GRW style theory of the collapse of the wave function, it turns out you could get rid of then the statistical postulate. You can't get rid of the past hypothesis. Many worlds, insofar as it's coherent at all, and as Barry mentioned, I have worries that many worlds is just not coherent because it can't produce an account of what quantum mechanical probabilities are about. But if you were to imagine that it's coherent, then the way the Mentaculus is going to work in the many worlds interpretation is very similar to the way it works in classical statistical mechanics. It'll have exactly the same structure. You will need a statistical postulate and you will need a past hypothesis, in addition to the microscopic equations of motion, which in the case of the many worlds interpretation is going to be just the Schrodinger equation. That is, the many worlds interpretation attempts to take this lemon that you're getting in quantum mechanics, that the measurement is going to produce a superposition of three outcomes and turn it into lemonade, okay, by declaring that no, there really are these three outcomes, and we're stuck in one of them. And that's why it appears to us as if the experiment has had only one outcome, when in fact it's had three. Okay, like I say, whether or not one can at the end of the day coherently make sense of a picture like that remains an open question, and I myself have doubts about.
So the other thing that I was going to mention, I was going to refer to something you said, David, as the analytic objection that just takes the past to be things that have already happened. And from talking many times with a fancy physicist that philosopher of physics that Barry might have had in mind, Tim Maudlin, mutual friend, I have the sense that he's one of these people that he thinks of time as really just something that's very fundamental and cannot be analyzed further. So I imagine that he objects to some of this, but
he objects to all of it. It's a whole other approach. We can talk about that at some point if you want, but he doesn't give an analytic answer to this question. He has a kind of metaphysics answer to the question about time. It's not a matter of meaning.
It's not.
But he does think. I mean, Barry is really the one who at a certain point explained Tim's view to Tim in a way that I know was very helpful to Tim and clarified things a lot for Tim. And maybe Barry wants to elaborate on that. But yes, Tim thinks that. I mean, Barry's right. It's not exactly analytic. But it is true that Tim would endorse a claim like, of course you can't affect the past. It's the past, okay?
Right, that's where I'm
of course the past is the only thing that you remember. It's the past, okay?
But he has a metaphysical explanation for it.
I mean, so talk about that a little, Barry.
So, you mentioned before we began that you're about to talk to Tim and Shelley. They will disagree with a lot of what we had to say. It won't be fair unless we're there to fight fair and square.
But I think he's going to talk to Tim and Shelley about Bohm's theory.
That's right. So this might not come up, but they disagree about how to think about probability and how to think about laws. But connected to what you were just bringing up about time, Tim thinks that time is fundamentally metaphysically different from space. So when David was bringing up this issue about, look, you'd be really puzzled if you could somehow influence things to your left, but not to your right. You want a physical explanation of that. Tim would want a physical explanation of that too. But about the past, he has a metaphysical explanation. It's that time passes. He thinks time flows. in some way. Well, he doesn't like it like that, because when I pressed him on that, he thinks that time, unlike space, has a built-in directionality in it. And that's needed in order to make sense of his conception of laws. But this is really a long discussion, which I've had, and it's in the journals between me and Tim and other people too. And there are arguments on both sides of this issue, but we're not going to get into this right now. But he has a metaphysical account that time, by its very nature, has a directionality in it, and it's that directionality that's going to explain these asymmetries of time. And
anyway, just shortly, Robinson, you're absolutely right that Tim is someone who represents a profoundly different approach to these matters than the one we're discussing here.
And Shelley, Shelley is, I think, most of the time he goes along with a Tim view about laws and stuff. He definitely has a view about typicality being more fundamental than probability, something I want to say a word or two more about in just a second. But then he gets into an argument, we get into a big discussion, he can be pulled in the more Humean direction. And then he says, what do you want from me? I'm a mathematician. He's a very good mathematician and a good philosopher too. Can I go back to the bit about when David was talking about most? David was motivating Boltzmann with the idea that a majority of the microstates, most of them, will behave in the normal way in one temporal direction and in an abnormal way in the other temporal direction. That's why we introduced the past hypothesis. But instead of talking about most, we introduced a probability distribution. I mean, that's the way to go. But a whole other approach just wants to take the notion of most as being more fundamental, because they recognize they got to go measure theoretic about that as well. I'm sorry, I live in a neighborhood where there's a fire station 2 blocks away. Can you hear that?
Actually, we can't.
Oh, good. Okay. Give me my ears. So they think to explain thermodynamics, statistical mechanics, and a bunch else, they want to make use of the notion of typicality rather than probability. I just want to give a nod in that direction and just put it aside, just so your listeners know we're well aware of it, and we all argue about this all the time. But it's really for another podcast.
Mm-hmm. Well, one reason I brought Tim up was that as you two were talking about the Mentaculus and time travel came to mind. And I did an episode with Tim and your student, Barry Craig Callender, and we did a whole episode just on time. And when I pressed Tim about time travel to the future, he would not entertain this at all, because he said, well, the future, and this was close to a year ago, so I'm paraphrasing and could be wrong, but he'd say, well, the future hasn't happened yet, so there's nothing to travel to. The only way to time travel to the future would be to just cryogenically freeze yourself or something like that, and then wake up once, I don't know if he would say the future is the present, but I'm wondering, since you have this fundamentally different view of past and future and time, if the Mentaculus can lend itself to discussions of time travel and possibly travel to the future. I know.
Yeah.
Okay.
I mean, the difference in our attitudes was nicely expressed in this poem that I attempted maybe inadequately to quote earlier. Time doesn't go anywhere. Time doesn't pass. Now, is it a possibility for there to be some worm-like thing that exists in the future with something like a state in which it has memories like mine, which are connected by lawfully with my memories now or thoughts or experiences now, well, that will depend on the fundamental dynamics of the world. And maybe general relativity allows for that. I don't really know.
But I'm puzzled here, and I'm puzzled by what you report Tim saying. You don't need general relativity. You just do the twin paradox. Okay.
Oh, good.
And the twin paradox is something of which, I mean, I was just reading it the other day, as it happens, of which Tim has a beautiful analysis in his book on philosophy of space and time. So yes, you could do it cryogenically. The other way you could do it is travel around in a rocket ship in such a way that much, much more time would have passed on Earth than has passed for you.
But that's not when people tell time travel stories, that's not what they have in mind. So what Tim should have said, that not only could he go to sleep, he could also go really fast for a while.
Right. Right.
But that's not what they have in mind when they talk about time travel. They have in mind the sort of thing I was talking about, where all of a sudden, I now can see the children that my 24-year-old son will have, or something like that. I probably won't be around to see them.
Rather than your brother's children or something like that.
Right. I could see the children of my other son who I had when I was 20, when I was younger than my younger son is now. I just saw them yesterday, but I won't be around to see my younger son's children, I think. But if I could time travel, I could. But I think, isn't it right that some people think that general relativity has solutions which would allow for that as a possibility?
Well, they certainly allow for time travel into the past. Which is usually what people worry is going to lead to paradoxes, where you kill your grandfather before you're conceived or before your parents are conceived. Or something like that. Certainly, there are solutions to general relativity that allow for that. Tim, I know is Tim's attitude towards the direction of time. I don't want to speak for his current thoughts about this. Last time I spoke to him about it, he does see a tension between that and these kinds of solutions to the to the Einstein equations. And
he should also be uncomfortable about naturalizing.
And he's tempted to suppose that those aren't genuinely, that those solutions don't correspond to any genuinely physical possibility. For that
his
reason.
metaphysics is ruling them out, and that should make him a little bit uneasy. I'm not saying it's a knockdown objection to it, but it should make them a little bit easier. Incidentally, I don't say that paradoxes that time travel to the future leads to paradox.
No, time travel to the past
would lead to getting rich if you could travel back.
Right. No, time travel toward the past leads to past. But anyway, Robinson, I'm sorry, we're getting off topic. In answer to your question, no, I don't. I mean, these kinds of solutions to the general relativistic equations of motion, certainly something like the twin paradox, is not going to pose any kind of special issue for the Mentaculus. It's going to fit right in. It's just one of the solutions that's going to emerge from the microscopic equations of motion. And even to the extent that we can make consistent sense of general relativistic kinds of time travel to the past, I don't see why those would pose a special problem either. Once again, these are just going to be features of the solutions to whatever the exact microscopic equations of motion of the world happen to be. There's going to be that slot for them in the Mentaculus architecture. They're going to lead to whatever kind of strange behaviors they lead to, but they're going to lead to those behaviors in the context of this general architecture. You're still going to need the microscopic equations of motion, the statistical postulate, and the past hypothesis.
Well, there will be issues because while the person is time traveling to the past, it'll still influence things in one temporal direction rather than the other. And there will be issues in sort of fitting all of this together. So I'm not sure that anybody has sat down and tried to work this out about how to.
I agree with that. I guess what I'm saying is, off the top of my head, it's not obvious to me what the conflict.
Yeah, I agree with that too. Sure.
Well, there are plenty more aspects of the Mentaculus that we could talk about. One is the contribution it makes to the literature on counterfactuals, but Barry and I spoke about that on our episode at length, and I'll be pointing that out in the introduction. So one thing we didn't talk about that I think would be neat to touch on, I think, David, you might have briefly, but how it relates to puzzles or questions about free will and agency.
I mean, Barry has a really nice spiel about this. It's going to turn out that, so the kind of account you're going to get in the Mentaculus of the fact that we take ourselves to be capable of influencing the future, but not the past, okay, is going to be, I think, very surprisingly, on the face of it, a matter of degree rather than a matter of a sharp metaphysical kind of distinction, okay? It's going to turn out to be the case that, if you evaluate a counterfactual, like suppose my finger were here instead of here at this time, okay? On the Mentaculus, that's going to change the trajectory that the world is on from t equals minus infinity to t equals plus infinity, okay? But it's going to turn out also that there are going to be many cases in which the trajectories associated with my finger being here and my finger being here toward the future splay out from one another very dramatically. Okay, so for example, if here is the button that launches the nuclear weapons and here is just some air, okay, the difference between my finger being here and being here at this time may have consequences toward the future that are as large as the difference between a nuclear cataclysm and the absence of one, okay? On the other hand, you're going to be able to show that the effect of the past hypothesis constraints is going to be to suck all of these trajectories very dramatically towards one another as you go back towards the past, okay? There are going to be very minuscule differences, okay, all the way back to t equals minus infinity, okay? But the way we're going to account on this kind of picture for our impression that by acting now we can influence the future but not the past is that although the counterfactual consequence of my finger being here as opposed to here are going to be different throughout all time, the differences between those consequences toward the past is going to be negligible and minuscule compared to the potential difference between those consequences toward the future. And that asymmetry is coming from the fact that we have a past hypothesis in one temporal direction and no corresponding, as it were, future hypothesis in the other temporal direction. But a really interesting upshot of this that Barry has pointed out and elaborated on, and maybe I'll just introduce it and then leave it to him, is that the fact that there is this influence toward the past makes one of the standard arguments for the incompatibility of determinism, of microdeterminism, with a robust metaphysical kind of free will, with a more than Humean kind of free will. is the consequence argument. Okay, that the consequence argument goes, look, if
maybe you should leave this one to me, David.
Okay, I'll leave this one to Barry. Anyway, just to introduce Barry's thing, it completely undermines the consequence argument. Barry,
yeah, so of course everything David was saying about negligible really is probabilistic, and that should be kept in mind in talking about this. But remember when we were looking at my T-shirt earlier, and I showed how the macroscopic histories of the world are indeterministic. That's what's being exploited here. As David was just saying, small differences in what's going on in our brains, which corresponds to different decisions we might make for a big difference in one temporal direction. In fact, likely will in one temporal direction, but not in the other. Because as he's saying, the past hypothesis sucks everything back into the low entropy state of the early universe. Incidentally, a point that maybe should have been emphasized earlier. When he's saying the low entropy, it's really, really, really low. And it takes some argument to show that this low entropy then actually has this consequence that in smaller, more or less isolated systems, like our bodies and so on, it basically has the same kind of consequences. Okay. So as the consequence argument is an argument it's an old argument, but it was made very famous by Peter van Inwagen. He's wrote a few books about it, which basically says, look, you can't influence the past, right? Yeah. What can we do about the past? Can't influence the laws, right? Yeah, you can't do anything about the laws. I mean, I would jump out my window. I can't say I'd like the laws to change so I don't smatter on the ground. It won't work. But you can influence the future. But the past and the laws, if determinism is true, entails the future. So Van Inwagen argued, and this argument goes, that you can't influence the future. But free will requires you being able to influence the future. So therefore, if determinism is true, you don't have free will. That's the way a rough sketch of this argument. I'm sure you can find people who give more sophisticated versions of it, but that's the basic idea. In the context of the Mentaculus, what you got to note is that you can influence in a kind of way the microphysical past, but you can't influence the macroscopic past because of this, what we were talking about before, that the macroscopic history of the universe pretty much will be the same no matter what decision I make. And if it were to be different in some counterfactual way, because a lot of it depends on how you're going to think about counterfactuals, it's not in a way you could know anything or care anything about. And you don't know about it, the differences it makes microscopically. But you can know, and you do care about the differences your different decisions can make probabilistically in the temporal direction away from the past hypothesis towards the future. So there is a kind of room for responding to the Van Inwagen argument. Say, look, it's right that you can't influence the macroscopic past in ways you care about, but we can give an account in which having alternative decisions involves influencing the microscopic past. Now, people who have this time flows picture are not going to like that. Well, let them deal with that. Or the past is settled view. But on this kind of general Humean framework about time and laws and probability we're talking about, you can influence the microscopic past, but we don't care about it. We never notice it. But in the Mentaculus picture, we can influence the macroscopic future away from the past hypothesis, and that we do care about. And we learned over time exactly how we can influence it, and because of the temporal asymmetry of knowledge. So we know a lot about the past, and in the past, when we've made certain decisions, we had such and such results. I know I shouldn't eat what I ate for lunch in the future anymore, but I didn't act on that. Okay, and so on. So there is, I think, and more generally, when I was reading David's Time and Chance, I was a very lucky guy to be his philosopher friend, to be reading this book, because I thought, and David can correct me here, because often I'm surprised that he actually learned a lot of philosophy when he was an undergraduate just from taking a great books course at Columbia. But I thought, boy, am I lucky, because I'm a philosopher, and I know that this is a gold mine for philosophers in this book. There's a lot of stuff that philosophers should know about from this, and this is one of them. It has this interesting consequence for this much discussed argument about free will in the philosophical literature. And I've written a little bit about that.
Okay. Well, as you two both know, I've been hounding and waiting to do this episode for a long time. And I'm so grateful that you two took the time to talk to me about the Mentaculus. So thank you so much.
It was fun.
Thanks for listening at all.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Earhart.